This lesson is on projectile motion that is launched at an angle. So consider an object launched at this point here with an initial velocity VO. This velocity will have the following components. We have the horizontal component, which we are going to call VOX, or initial horizontal velocity, and the vertical component, or VOY, or initial vertical velocity. In some text, VOX is also called as VIX, whereas VOY is also the same as VIY, or initial vertical velocity. Now, with the angle theta with respect to the horizontal axis or the x-axis, we can say that the initial horizontal velocity VIX is just equal to the initial velocity VI multiplied by cosine of the angle theta. On the other hand, our VIY would be equal to VI sine theta, or the initial vertical velocity is just equal to the initial velocity VI multiplied by sine theta. Now, as the projectile goes up its trajectory, if you notice, the horizontal component of the velocity remains the same. So the length of the arrow doesn't change. So the horizontal component actually is constant. Let us write that down. So horizontal component, this is constant. In such a manner that instead of just writing VIX, we could just say VX is equal to VI cosine theta. And once again, this is constant all throughout. So whatever our horizontal velocity is initially, that would also be the same as the final horizontal velocity, because once again, the horizontal velocity is constant. It doesn't change. So in this case, since horizontal velocity is constant, we could also say that the acceleration on the x-axis is 0, because once again, Vx is constant. On the other hand, if we look at the vertical component of the velocity, or this arrow right here, as the projectile goes up, the vertical velocity actually decreases, as being represented by the decreasing length of the arrow. It decreases until such time that it would reach the maximum height, wherein the vertical velocity here is 0. So once again, at the maximum height, the vertical velocity is 0. Let me write that down. Now, as the object reaches the maximum height, the vertical velocity is 0. But then, at this point here, when the projectile goes down, if you notice, the vertical velocity starts to increase, but in the negative direction. So as the vertical velocity, as the projectile goes up, the vertical velocity decreases until such time that it reaches the maximum height, where the vertical velocity is 0. However, as the projectile starts to go down, the vertical velocity increases, but in the negative direction. Then we could say that the vertical component of the velocity, let me write that down here, the vertical component Vy is changing. Therefore, that there is acceleration in the y-axis. So if we say that there's no acceleration in the x-axis because the horizontal velocity is constant, there is acceleration on the y-axis because the vertical velocity is changing. Now, what is this acceleration? This acceleration, in fact, is the acceleration due to gravity, or equal to negative 9.8 meters per second. So this acceleration, once again, is acceleration due to gravity, which is symbolized by the symbol g, and that is equal to negative 9.8 meters per second square. And take note that this acceleration due to gravity is actually constant. In fact, projectile motion is an example of uniformly accelerated motion. So once again, g is constant acceleration. This means to say that from the point at which the object is released, meaning to say at this point right here, the object will already experience this acceleration of negative 9.8 meters per second square, and that is directed downward. So there's acceleration there equal to g. There's also acceleration here at any point in the projectile's motion. It would always experience this downward acceleration of negative 9.8 meters per second square. So this acceleration is constant. Now, recall that for motions with uniform acceleration, the following equations apply. So we have v final is equal to v initial plus acceleration times time. So if we are going to write this with respect to the vertical axis, because it's only the vertical component of the velocity that is accelerating, so we could say vy final is equal to vy initial plus the acceleration. Instead of writing a, we could write g, because the acceleration on the y-axis is just equal to acceleration due to gravity, and that is equal to t. Furthermore, we have delta x, or the horizontal displacement, is equal to vit plus 1/2 at squared. So if we write this again in terms of the vertical component of the projectile's velocity, then we say instead of delta x, we are gonna be referring to the delta y, or the displacement along the vertical axis. So we say delta y is equal to vy initial multiplied by time plus 1/2, and again our acceleration is going to be the acceleration due to gravity g multiplied by the square of time. So once again, if you notice, the only difference here is instead of x, we have our y, and instead of just simply putting vi, we put vyi, or the initial vertical velocity. And lastly, we have vf squared is equal to vi squared plus 2a delta x. So as we write this with respect to the vertical component of the projectile's velocity, we could say y final squared is equal to vy initial squared plus 2. Again, the acceleration would be equal to g, or the acceleration due to gravity, equal to negative 9.8, and instead of having delta x, we will have delta y. Now, having these equations, you also need to remember that your initial vertical velocity is equal to vi sine theta. And therefore, we could actually write this equation, as vf or vyf is equal to, instead of having vy initial, I could just simply write, or I could also write vi sine theta plus gt.